7 main mechanisms to know. Obviously, the two hardest ones. I think we are live on YouTube now, guys. I think we are live on YouTube. We're going to be going over some questions, but mainly the content. Today and tomorrow morning, we're going to be going over the content of A-Level Chemistry Paper 2 for OCRA. So yeah, we're just going to do as much as we can today. I will be drawing out the mechanisms if possible. Started a little bit earlier today because I just wanted to get people's opinion on drawing out or basically the setup and how I should present certain mechanisms. We are live on YouTube, guys, if you want to do A-Level Chemistry Paper 2 revision. I'm sure you guys have been banging out past papers all day, but if you guys want to like a chill kind of going through all the content, maybe some small little details, there's 1, 2 markers that you haven't. How long? How long? It's a good question to be fair. I haven't really thought about how long. Kind of just thought we're gonna get through as much as we can, see what we can do. To be honest, right now I have a name the molecule question and asking you guys to tell me or draw out all of the C5H10 isomers. Two pretty key things. Remember, guys, when we have something in the general formula of CnH2n, it's either going to be cyclic or it's going to be an alkene. That's very key to remember, guys. A lot of people forget for example, there was a question previously, I think it was C6H12, and a lot of people didn't realize whether it should be an alkene or two alkenes, or if we're going to have cyclohexane. So it's good to remember those little things. We're just going to be going over content, guys. If anyone's on YouTube, feel free to drop the name of this organic molecule that I currently have on the screen. Feel free, feel free. How long are you gonna be? We're gonna just we're gonna go. I don't know how long it's gonna go. We're just gonna do as much content as we can. Just gonna make sure the stream is in good condition before I start going through anything. We're gonna start going through stuff at 8 o'clock, I reckon, maybe 8:05. If anyone's watching, feel free to drop the name of this molecule in the chat. But yeah. Ooh, almost revealed it. Can you sit my exam for me? No, you'll be fine. You'll definitely be fine. Almost done. 1 more week. I know for the STEM students, there's a lot of exams on YouTube, guys. We're live on YouTube. We're live on YouTube. I'm going to be going through mechanisms, going through content as much as we can today and as much as we can tomorrow. I don't have an Apple Pen or OneNote, so most of it is pre-drawn. Some of it I'm going to try to draw if you guys are fine with it, but we'll see. We will see. Revise in the day or in the 2 years. It's never too late to revise. So guys, these are the 2 warm-up questions I have. Nothing too tricky, nothing too tricky. But yeah. Let me know if everything's good, guys. And I'm also going to draw out a mechanism before we start this whole thing. And I want some feedback to let me know if it's too slow, or if you guys want it a little bit faster, or if I just show you the pre-drawn mechanisms for each one. But organic chemistry is just a memory game. You know, we saw last year was 92 for an A star. Can you stream on YouTube? We got the first answer. I won't reveal the answer just yet. But 1-methyl 3,4-dichlorohexene. It's looking pretty good to be honest. Chloro before methyl. Chloro before methyl, guys. Remember, alphabetical. It's not in the order of the numbers. It's in the order alphabetical order. And we do that. Exactly. Alphabetical order. But you did get the numbers correct there. So that is indeed. Let's see if I can quickly switch between our 2 tabs. 3,4 dichloro 1-methyl hex. You don't need the hex 1-ene. You can do hexene because it implies it's in the first position. But I wrote out 1-ene. There's no harm putting extra numbers. In all mark schemes, they will always allow you to put the extra numbers. Guys, we're not starting just yet. Gonna wait a few more minutes before we start going through the content. But yeah. Where's the question? Looks I'm asking for paper 1. That's good to hear. Where's the question? All the questions are on YouTube. I won't be going over too many questions today. I'm going to be going over mainly content. So it looks like you guys are happy with this molecule. Looks like we're all happy. Okay. This is kind of just me experimenting with OneNote before we start going through everything, guys. I don't have an Apple Pen, so it is a bit of a pain. I'm going to erase this molecule now. And I want you guys to order these in terms of the boiling point. I'm going to put them in a certain order, and all I want you to do is just kind of tell me one, two, three, four, five. Okay. So whichever from the lowest to the highest boiling point, if it lets me. I'm really just practicing with OneNote, guys. I apologize if it is just horrendous. If it's horrendous, we're gonna ditch it and just. I have all the notes already prepared, so I wouldn't stress too much. Right, guys. So I'm gonna give you five organic molecules. Just tell me the order of boiling points. Five organic molecules. We will be going through the content a little bit faster, guys, as we go on. Just for now, I am gonna be just warming up and practicing with OneNote because no Apple Pen is a killer. I will not lie. All right, boys. In the order you see them from left to right, from beneath my face. Got one, two, three, four, and five. Tell me the order of the boiling points. What are we saying? Some people saying to the highest, some people. So left to right, guys. Starting with your methyl propane on the left. So this is number one. All right, amine is all the way. It's number five. Just tell me the order, guys. Tell me the order. This is all warm up, guys. We will be going through content a little bit faster in a minute. How to get good at mechanisms. Link in bio for my channel, guys. Link in bio. Okay. I'm just waiting for everyone to join, guys. It is just a bit. Four, five, two, three, one. So you're saying four is the highest. Highest boiling point is four. Then you're saying five. Then you're saying two. Then three. Then one. I will reveal in a second, guys. Four, five, two, three, one. Four, five, two, three, one. I can tell you right now, guys. I'm gonna start drawing on. Gonna start drawing on the highest, and then we're gonna go on from there. I'll tell you now. OneNote with no Apple Pen is very annoying. If it's too slow, do tell me, guys. I do apologize. Okay, so I'm going to name number one will be the highest boiling point, and then we're going to go down from there. So highest boiling point will be oxygen, or will be oxygen, sorry. Will be our propanol. Then from there, because it's actually killing me, this one note. Just getting the hang of it. I'll get used to it as we go along. Tried to practice before. It's always a little bit tricky. Then from there, guys. This is our order, guys. This is our order. I'll explain why. Four and two both have hydrogen bondings because our hydrogens are attached to those electronegative groups, either oxygen, nitrogen, or fluorine. Okay, but here's the thing, guys. So both of these have hydrogen bonding. However, with our propanol, oxygen has two lone pairs. So think about drawing that hydrogen bonding. We're gonna have two lone pairs of that oxygen, which will be attracted to delta positive hydrogens from other water molecules it's surrounded by, okay, or other, in this case, propanol molecules. Then we have our amine. Because nitrogen only has that one lone pair of electrons, the hydrogen bonding will not be as strong. Remember, these two will also have London dispersion forces as well. Okay, very key to remember. Then, because let me see if I can actually draw on here. It might be a little bit easier. We're not properly going through the content yet, guys. Okay, then here because we have that polar bond, because the electronegativity of our chlorine, we're gonna have permanent dipole-dipole interactions as well as London dispersion forces. The chlorine might be branched, but we have that permanent dipole-dipole interaction. Sorry, permanent dipole-dipole. So we have that permanent dipole-dipole intermolecular forces, stronger than London forces, more energy is required to break those bonds. And with these two, that's where the branching argument comes in. Exactly, it's polar. For OCR, which doesn't come it's branched. No, we also need to know hydrogen bonding, and they could give you something like this, because we need to know about those permanent dipole-dipoles. It's three types of intermolecular forces. London dispersion forces, permanent dipole-dipole, and hydrogen bonding. They go increasing strength in that order. And remember, all of these will also have London dispersion forces. Chlorine is more electronegative. Exactly. Exactly. That OH will be a higher boiling point because it has two lone pairs of electrons. It's very key to know. Exactly. Exactly. And then because our butane is not branched, unlike our methyl propane, have more surface points of contact, stronger slash more London dispersion forces, more energy required to overcome and break these. But that's exactly it. Can we see your notes? Yeah, yeah, guys. All my notes are gonna be. I'm gonna be going through the content on my notes, okay? But it's not very neat. So I warn you now, guys. I warn you now. Just as I go, I'm gonna be kind of clearing this, and I will be drawing mechanisms. I'm just getting the hang of it now, guys. It will be a lot faster once we properly get going. Just a few warm-up questions while people join up. There are the notes, guys, if you guys want to make quick notes. And also all of those C5H10 isomers were here. We had the unsaturated and the saturated, where we had that cyclic, yeah, we had the cyclic isomers and we had the unsaturated organic molecules. Exactly, this paper is completely just memory. We are going to start going through the content in just a second, guys. Today is more module 4, so if you guys are comfortable with the content and more comfortable with module 4, do not stress too much about today. Alright, guys, I'm just going to start going through the content now. 8:05. Alright. So start with alkanes, free radical substitution. I'm going to talk about ozone because it's linked to free radical substitution. Okay. So we've already gone through this, guys, explaining the trend in boiling points. We know that ethane and butane and methyl propane. Ethane having that shortest carbon chain, it will only have London dispersion forces. We have no dipoles, no polar bonds here, and we also have and no hydrogen bonding. So ethane will have a lower boiling point than both butane and methyl propane. Comparing methyl propane and butane, methyl propane is branched. We have less surface contact points between the molecules. Okay. We also know with the ethane we have a lower number of electrons, therefore have the weaker or fewer. You can say weaker or fewer London dispersion forces due to having less electrons. You could also say smaller MR, but you do have to mention weaker, fewer London dispersion forces. Less energy is required to overcome these forces in ethane to boil the sample, and it's the same thing for methyl propane due to the branching. Drawing pi and sigma bonds, I can draw you a pi bond right now. Because I will be speeding up as we go. Yeah, let's draw some pi bonds. They are actually part of this as well, but I'm just gonna make sure this is all good. Okay. So drawing those pi bonds, guys. Just make sure everything's in the screen. Okay. So drawing those pi bonds. I'm actually booking out right now, guys. Sorry. OneNote is killing me. It's actually annoying. Okay. There we go. I do apologize, guys. I'm gonna keep getting faster as we go. So remember, guys, pi bonds are the sideways overlap of p orbitals. Sideways overlap of p orbitals. That's the one marker they're going to ask you. And we know p orbitals, dumbbell shapes, above and beneath our carbons. So this is the first thing you're going to draw in the exam. We did see one past paper question like this, but it could change. It could change. They could bring it back. They could definitely bring it back. And because we have this sideways overlap, this is disgusting drawing, guys. I actually apologize. Guys, I'm writing with my finger, okay? If you guys don't want me to use OneNote and you think it's too slow, just let me know in the chat and I'll just go through the content. But then because we have the sideways overlap of these p orbitals, we have these bonding regions above and below the bonding atoms. That's the key thing, guys. Sigma bonds are between the bonding atoms, that area of electron density, whereas pi bonds are above and below, okay? We are going to get there. I'm just going to start going through all the content, guys. Just have it all at once, okay? Just going to make sure the stream isn't dying. Too slow? Okay, too slow. Yeah, fine. I did think it was too slow. All right. Let's just go over the content. I'm probably going to ditch the OneNote until the end. All right. So we've already gone over this branching. Let's just carry on. I know this is year 1 stuff. Let's just go on quickly. So for combustions, we have to know that alkanes are mostly highly flammable. In excess O2, we're going to form carbon dioxide and water. My tip when balancing combustion equations, this is OCR. My tip when balancing combustion equations, balance your carbons, then your hydrogens, then your oxygens. The other thing you have to know in the exam is just know that methane is a gas. I'm sure you all know this already, but you have to know it going in. It's the only one you really need to know out of all the alkanes. So here's just an example, guys. If we have our methane in oxygen, we form carbon dioxide and two water molecules. Nothing tricky here. In a limited oxygen environment, alkanes undergo incomplete combustion, produces carbon monoxide. This is toxic. You may be asked to produce an equation. Okay, we will do module 6 tomorrow and probably get onto it today. Okay? Free radical substitution, guys. Free radical substitution. If we're going from a haloalkane, if we're going from an alkane to a haloalkane, we're going to be using free radical substitution. What do we need? UV light and a halogen. So alkane to a haloalkane, exactly that. The alkane reacts with halogens in UV light. What happens? We have homolytic fission. Each atom in the bonded pair receives one electron from that shared pair of electrons. You have to know that. We break the covalent bond. Each atom in the bonded pair receives one of the electrons each from the shared pair of electrons. You have to know that. So our products with a haloalkane, going from an alkane, under UV light with a halogen, you get a haloalkane and a hydrogen halide. So the mechanism, guys, free radical substitution. We have initiation, 2 propagation steps, and termination steps. Okay? Initiation step, UV light, we have that homolytic fission of the bond between the halogens. Yeah, it could be chlorine, it could be bromine. They will ask you to do it. Almost definitely guaranteed in the exam. Okay? So we're going to go over each up, guys. Going over propagation, we have our chlorine molecule, simple molecule, and we get 2 chlorine radicals because that homolytic fission, the dot represents an unpaired electron. Then we have this chain reaction with our radicals. So naturally, because we have that chlorine radical, we start the chain reaction, and this chlorine radical acts as a catalyst. Okay, it will catalyze the destruction of ozone, but we're going to get onto that in a second. 400. Okay. So we would have our methane with that chlorine radical. We produce that CH3 radical, have that dot, so that's our unpaired electron, plus HCl. Remember, guys, we're always going to have in our propagation steps a radical on the left and a radical on the right. And then the radical that we get from that first propagation step goes into that second propagation step. We react it with our original halogen, Cl2, and then we get exactly what we need, that chloromethane, and another chlorine radical. So these are propagation steps. From here, guys, we have our termination step. We combine 2 free radicals, and we pair up our radicals to form a molecule. In this case, basically, okay, so in these questions, guys, you're going to have to make normally these termination steps, and they may ask you for a specific termination step to make a specific molecule. You do need to know this. OCR, you need to know this. So combining 2 radicals, we pair up our radicals to form a molecule. 3 possible options in this specific scenario. We can have 2 chlorine radicals, we can have 2 CH3 radicals, or we can have a CH3 radical with a chlorine radical. So our products will be Cl2, C2H6, and CH3Cl. The common question, guys, that I mentioned here is they may ask for a termination step that forms a molecule with a certain MR. They do like to do that, guys. They do like to do that. Unfortunately, I've shown it here. What are the problems with free radical substitution? We need to know these. These are 1-2 markers, but they always ask them. Well, I say always. They tend to ask them. So one problem is further substitution can take place. Think about it, guys. We have more radicals still in our reaction. They can continue reacting with our products after these termination steps. Our CH3Cl could go on to react with another chlorine radical. Another problem with free radical substitution is we get a mixture of products. And also, if you want your halogen in a specific position, substitution could take place at a different carbon atom. So this won't go the side. Another thing to think about. So for example, we could get CH3Cl, Cl2 goes to CH2Cl2 plus HCl. But this can continue happening. We could eventually get 4 Cl molecules and lose all our hydrogens. So we could have CCl4. Do you get penalized for putting the radical somewhere else? No, the dot can go anywhere, but I'm just putting it where it actually is, where that unpaired electron actually is. So that's free radical substitution, guys. I'm going to go over quite quickly module 4, and then we're going to kind of spend more time on module 6, because I know that's more relevant stuff and a lot harder. So next thing, guys, we're going to talk about free radical substitution and CFCs destroying ozone. Can you say multiple terms? you can say, but that's kind of the mixture of products idea because we can get all these different termination steps. We'll get that mixture of products by the end of it. But yes, you can say that. So going over ozone, guys, in our atmosphere we have this equilibrium of O2 plus O, and then O3 on the right hand side. Okay, nothing scary here. So now we're going to focus on how CFCs lead to the destruction of ozone. So guys, which bond in our CFCs breaks? Which bond in our CFCs break? Let me know, let me know. Exactly, you get substitution at another place on the carbon chain, or with free radical substitution, you get further substitutions. So eventually, starting with methane, you could already have tetrachloromethane, for example. Let me know, guys, let me know which bond breaks on our CFCs. I'm just going to go through it, the chat is a bit delayed for me. So that initiation step on our CFCs, they will not give you the same CFC as you've seen in past papers. Exactly, it will be the chlorine radicals, exactly. So that weaker carbon-chlorine bond is broken by homolytic fission. So we're forming our radicals, homolytic fission. I'm going to keep saying it because they like to ask these things. Breaking of a covalent bond, where each of the bonded atoms receive one electron from that shared pair of electrons. Exactly, it has a lower bond enthalpy as well. That's very key. We're going to get onto haloalkanes in a minute, but it does have a lower bond enthalpy. So as we know, the chlorine catalyzes the breakdown of ozone. So we have this initiation step. I should probably use the light here. We form two radicals. They can also do this, guys, with NO2, forming an NO radical and single O. Absolute same thing as chlorine, guys. Absolute same thing. So I would recommend just memorizing this equation for the exam. We have a chlorine radical reacting with ozone, O3, forming a ClO radical and O2. Remember, guys, catalyzing the breakdown of ozone, we have O3 plus O goes to 2O2. So you can always check your answers if they give you an unknown radical to break down or causing the destruction of ozone. You know it's going to give you this overall equation. So you can almost check your answers by using this overall equation. So we do have a chlorine radical that we created from the homolytic fission of our CFC. Reacting with O3, we have that ClO radical plus O2, and that ClO radical plus a single oxygen, another thing that we have in our equilibrium at the start, goes to that chlorine radical. So that chlorine radical is reformed, guys. We've reformed the chlorine radical, therefore it acts as a catalyst. We know something is a catalyst if we reform that catalyst. Plus that second O2. So we have our overall equation of O3 plus O goes to 2O2. This live, I'm not sure, guys. This live might be a while. The two propagation steps is if we were using NO2, would be our NO radical plus O3. Same idea, guys. O3 in one propagation step, single O in the other propagation step. So we form that NO2 radical with an oxygen, then we have that NO2 radical plus that single oxygen, reforms that catalyst, that NO radical, and O2. They may ask you guys some uses of CFCs. Normally it'll only be one or two, but you should know that they're used as propellants, aerosols, refrigerants. Why? Because of their stability and low reactivity, and they're non-toxic. This is a very key thing to know. Could be a cheeky one marker. And as we know in organic chemistry, I believe it was 92 or 93 for an A star last year. So definitely an important thing to know. Definitely important. You need to get every mark you can. Can you write it overall as 2O3 goes to 2O2? You have 4 oxygens on the right and 6 on the left, so I assume not. Is there a termination step? Yeah, it will be the same termination step. Oh no, in this one no, because we're forming that oxygen. You would get termination steps in general. You would get radicals reacting with radicals, but for the specific destruction of ozone, these are the two key propagation steps to make that overall equation. You will get termination steps. That's not part of the overall equation. Yeah, exactly. It doesn't quite add up. Doesn't quite add up. Okay, guys, so that's alkanes, free radical substitution, and the destruction of ozone. Let's continue on. We're gonna go to alkenes. Are you guys, give me a thumbs up if you're happy with this format, or if you prefer me to use OneNote. Or should I just use OneNote for mechanisms? Let me know mechanism if you want it for mechanisms. And just let me know how we're thinking. It's very slow. I don't have an Apple Pen. I do apologize. Or do you guys just want me to go over it like this, so we can just get through as much content as possible? Let me know, guys. Let me know. This is good. Okay. This is better. Okay. Yeah. Cool. All right. Calm. I had the feeling the OneNote was not going to work with no Apple Pen. Okay. Let's just do this. I guess it is more of a memory game, so we have to just go quickly. So alkenes, exactly as you guys were asking before, sigma bonds and pi bonds. Let's think about it. All sigma bonds are is the overlap of orbitals, sorry, between bonding atoms. So the area of electron density is between the bonding atoms. Pi bonds, the sideways overlap of p orbitals instantly is above and below the carbon atoms in that alkene. Okay, as we said, it's not. Remember, guys, it's not two bonds. Sometimes people will see that overlapping of the dumbbells, sorry, the p orbitals, and they think we have a bond beneath and below, above and below, sorry. But that's not the case. It's just one bond. Okay, everyone's happy. Know this for everything, got it. So this is what you would draw, guys. If you have to draw out your p orbitals, the sideways overlap, and then your alkene, this is what you do. So they ask for this alkene, they want you to talk about the p orbitals sideways overlapping. This is what you would draw. You can see in a past paper, but you gotta know it. They could ask it again. No one says they can't ask it again. Alright, guys. Before I scroll down, tell me what stereoisomerism is. Write down the definition. They've asked it in like 3 or 4 past papers, I believe. You gotta know it. I'm not gonna carry on yet. Just gonna leave this p orbital thing until someone tells me what stereoisomerism or isomerism is. Let me know, guys. Let me know. Exactly. In ethene, there's one pi bond. That double bond is a pi bond and a sigma bond. So if we see a double bond, that's plus one pi bond plus one sigma bond. Yeah, okay, five sigma, fine. But I'm just talking about the double bonds. Yeah, it would be one, two, three, four, five. Same structure forming a different arrangement of atoms in space. Same structure forming a different arrangement of atoms in space. Same. Okay, that's exactly it. Same structural formula, guys. Structural formula. Same structural formula, but different arrangement of atoms in space. Exactly that, guys. I'm going to be doing this interaction thing. I know it's a bit slow. I would say it's going to be about 93 for an A star. Yeah. The reason we see stereoisomerism or isomerism, however you want to say it, in our alkenes is because that carbon-carbon double bond is unable to be rotated. It is locked in place. That's why we can see EZ and cis-trans isomerism. So as a result of this, if it lets me scroll down, it's always stubborn with me. There we go. So alkenes can demonstrate EZ isomerism. What is a requirement? Each carbon involved in that double bond must be bonded to at least 2 different atoms or groups. Okay? It's really not letting me, guys. So give me a sec. Okay. Alright, cool. So exactly that, guys. If we want to see that EZ isomerism, has to be that asymmetrical, and we have to see each of them bonded to 2 different groups in that carbon-carbon double bond. Okay. For cis-trans, it's a special case of EZ if we have one of the same groups attached to each of the carbons. For example, we have a hydrogen on the left, hydrogen on the right carbon, and they're both either above or below the carbon plane. Then that'll be cis. If they're opposite sides, then trans. I do have a very key thing to talk about, guys, with these the CIP rules. Okay. So here we have it, guys. The highest priority groups, these CH3s, opposite sides of the carbon plane. Okay. Opposite sides of that carbon-carbon double bond, guys. This is going to be E, but it's also going to be trans because you can see they both have this CH3 group and they both have this H. There are opposite sides, going to be trans. Then for our Z isomer, highest priority groups, they're on the same side. That's all it is, guys. EZ can be longer, definitely something to consider when making alkenes. But definitely important, definitely important. So guys, I wanted to go over this. A lot of people get a little bit confused when assigning highest priority groups. So all it is, guys, you have to look at the atom that's directly bonded to the carbon, and then directly bonded to the next if it's the same on each one. So here you can simply count each of our carbons. So let's focus on this right carbon first. This is attached to a carbon here, MR, sorry, has 6, yeah, and then H is 1. Let me get my data sheet out just to make sure I'm not chatting. Okay, so carbon is 6 and hydrogen is 1. Okay, same idea here. Carbon is 6, carbon is 6. We cannot do this, so we're going to have to move on to the next step. We have to see the atoms that carbon is directly bonded to. We have a hydrogen and a bromine, then we have a hydrogen and a chlorine. Okay? Because that bromine, is everyone good? This paper is very good. No, it's fine. So therefore, we're going to have a higher priority group with the bromine. Or you go to that next bonded atom. You don't keep going towards the whole chain, you go to the next bonded atom, okay? NMR will be tomorrow. I'm actually be going through NMR quite well. So a little bit of a harder example here, guys. So on the left carbon here, we can clearly see the CH3 will be the highest priority group. But then we have to find the subtotal. So immediately going to the next bonded atom, we have the carbon. And we have the carbon here. So these are the same, we have to move on. Looking at the atoms that are directly bonded to the carbon. So looking at the top first, we have 6, and then we have 2 hydrogens. That's plus 2, that'll be 8. Going beneath, we're directly bonded to a carbon, another carbon, and a hydrogen. This is going to be 13, okay? So the key thing is to find the subtotal of the atoms bonded to the carbon. So therefore, our high priority group will be this bottom group here. So they will be on the same side. Zusammen, if you want a German, so it's going to be a Z isomer. Longest carbon chain, 1, 2, 3. Oh, it's going to be a methyl group as well. Can't be asked. Guys, name it if you want. We can actually quickly name it if we want. Guys, drop the name in here. What's the difference of trans and E? You can have trans and E, you can have cis and E. They don't, just because you have cis doesn't mean you can't have Z or E, they're all the same. You can have any combination with any of them with each other, okay? It's a special case of EZ when you have that same group, for example, a hydrogen or a CH3, for example, on each of those carbons involved in the double bond. What determines priority? Those are the CIP rules. You go along the chain, one by one, just seeing which adds up to the largest subtotal. Go carefully along the chain. Can't see the compound properly. So you have to look directly, the atom directly bonded. Do not look at the full chain, look at the atoms directly bonded. Cis and trans when 2 different groups are the same. So example of trans and cis with E and Z, we can see here we have a Z isomer because the highest priority groups are on the same side of the carbon plane. But we can also see that's going to be trans because each carbon involved in this double bond has a bromine attached to it. These bromines are on opposite sides, therefore it's going to be trans. So we have a cis trans because each carbon has the same substituent group. Just going through all this, guys, slowly. Let me know if anything is confusing. Key thing to know about sigma and pi bonds: sigma bonds are stronger than pi bonds. We need to know, as I mentioned before, that double bond has 1 sigma and 1 pi bond. Sometimes they'll ask you in a question, they'll give you a big organic molecule, they'll ask you how many sigma bonds, how many pi bonds. Exactly here. So if we would count the number of sigma bonds and the number of pi bonds, I'd always recommend drawing out displayed, not leaving it in the skeletal. So drawing out displayed, count every single bond, and the double bond will also be 1 sigma bond. So we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 50. And the only pi bond will be 1 pi bond on that double bond. This live stream will be available later. Alright guys, we do have a mechanism here. It's going to be electrophilic addition. First year stuff, nothing too tricky. So what is an electrophile? Electrophile is an electron pair acceptor. Electrophilic addition, we're going from an alkene to a haloalkane. Okay? This can either be for a hydrogen halide or just a halogen. So looking at this example here, if it lets me. So we currently have ethene and we have bromine, okay? Remember, bromine, there isn't any natural differences in electronegativity. So this area of electron density will induce a dipole in our bromine. So bromine, one of them will be partially negative, one will be partially positive. We have a lone pair. So we have that curly arrow going from an area of high electron density to an area of a low electron density, going from that carbon-carbon double bond to that partially positive bromine. Then the bond in between our bromine atoms will undergo heterolytic fission. Okay, so both of those shared pairs of electrons will go to one of the bonded atoms. So from here, guys, we form that carbocation. Here we do not have to worry about carbocation intermediate stability because each carbon is just attached to 2 hydrogens. Okay, so exactly that, guys. The dipole on the bromine is induced by that carbon-carbon double bond because of that high electron density. We have this intermediate carbocation. It doesn't matter which side because we don't have primary, secondary, or tertiary We just have two primary carbocations that would be, so we don't have to worry about that. And then we get this 1,2 dibromoethane. Yeah, get OH sigma. Okay, cool. Testing for an alkene, guys, you have to know it. We use bromine water, it will decolorize bromine water. Next one, guys, we're going to go to hydrogenation of an alkene to an alkane. You have to know that this uses hydrogen, nickel catalyst, and 150 degrees. Remember, this is the case also for nitriles. If you have a hydroxynitrile or a nitrile or an alkene to an alkane, you're going to need hydrogen and a nickel catalyst. Okay, that's always the same for all of those. So it's kind of good to remember whenever you're adding all those hydrogens, it's just going to be nickel catalyst and hydrogen. Another key thing to remember, guys, in these addition reactions, it's going to be 100% atom economy. Double bond has one pi and one sigma bond. Now, guys, same idea as before, alkene to a haloalkane with a hydrogen halide. With a hydrogen halide, we're already going to have that difference in electronegativity. So there's already going to be a polar bond. A halogen will be delta negative because it's more electronegative, and a hydrogen will be delta positive or partially positive as it's less electronegative. Now, the key thing, guys, is we can get structural isomers. Okay, so if we have this hydrogen iodide with but1ene or butene, we can get either the iodine in that second position or in that first position. Guys, tell me right now which one of these will be the major product. Which will be the major product? Let me know, guys. Let me know. The major product, which one will be? So which one will form that more stable intermediate carbocation? Which one, guys? Which one? Let me know. Let me know. Let me know. 2 iota, 2 iota. Exactly that. Because this carbocation will be a secondary carbocation because that carbon, the positive carbocation, will be bonded directly to two carbons. That 2-iodobutane will be our major product. This is electrophilic addition. This is just first year. Looking at that mechanism, we have to know the mechanism, guys, because we have that more electronegative chlorine. It will be partially negative, whereas a hydrogen will be partially positive. So we have that curly arrow. So I did use the example here. Looks like I went a little bit inconsistent, guys. I had an alkyl group. This should be a hydrogen. So this is delta negative. We have that heterolytic fission with both electrons in that bonded pair, breaking the covalent bond, going to that chlorine. So we're going to form that chloride ion and the hydrogen with that curly arrow going from the area of high electron density to low electron density from that double bond to that partially positive hydrogen. We're then going to get this carbocation intermediate. In this case, it won't matter. Then we're going to have curly arrow going from the lone pair of electrons. Remember, curly arrows show the movement of a lone pair of electrons to this positive carbocation. Then we have our chloroethane. Alright, now we're going to talk about carbocation stability, guys. It's Markovnikov's rule, as we know. We have primary, secondary, and tertiary carbocations. As we know, primary is the least stable, tertiary is the most stable. The most stable is always preferred in mechanisms, so that will be the major product. As I said, the major product will always be the most stable route, and the minor product will be the least stable route. Let's go for an example, guys. This is the one we had before. If we have that hydrogen halide, in this case, hydrogen bromide, if it lets me go down. So here we have propene. Same idea as before. Because the bromine's a lot more electronegative than the hydrogen, it gets partially negative. We have that heterolytic fission, breaking that covalent bond with both lone pairs of electrons going to that bromine. We also have curly arrow going from high electron density to low electron density, attacking that partially positive hydrogen. From here, this will be that stable carbocation because we have, let's see how many carbons it's connected to, 1, 2, that's as a secondary carbocation. If we had used the other carbon, this would just be a primary carbocation. This is more stable, so our major product will be 2-bromopropane. Then we can see our minor product, where we only had that primary carbocation, will be 1-bromopropane. Nothing scary there, guys. Alkene to an alcohol, alkene to an alcohol. Alkene to an alcohol. So the reactions that we need is steam and a phosphoric acid catalyst. We can also have sulfuric acid, but I think phosphoric acid tends to be the one they tend to tell you in these papers. So all it is, guys, we have to be very aware of the structural isomers and the major and minor products once again. All we do is because we're adding H2O. We're going to add a hydrogen to one of our carbons and an OH to the other, going from an alkene to an alcohol. This is also at 300 degrees, guys, but nothing, you don't need to know that. You tend just to have to say with heat. So continuing on, going on, addition polymers. We form addition polymers, under high heat and pressure. The alkene group polymerizes. This will be the addition polymers. We can have condensation polymers and addition polymers. When it's an alkene, so we have that carbon-carbon double bond, we're going to form addition polymers. So exactly that, we go from an unsaturated monomer, alkenes, to a long-chain alkane polymer. So we'll have N monomers, alkene monomers. And all we have to do, guys, get rid of that double bond. I'd always recommend to put those hydrogens vertically up, makes it look a little bit nicer for the bracket sound. Extend those bonds from your carbons, and then we have N of these. They may ask you to draw 2 repeat units, 3 repeat units, whatever it is. But that's exactly it. And as I have said, we only ever show 2 carbons in the line between brackets. Just makes it a little bit easier for that single repeating unit. So carrying on, guys, going on to alcohols now. We're just going to keep going through as much of the content as we can. Alcohols and a bit of reflux and distillation. Guys, you gotta tell me what is the color change we see when we oxidize alcohols and what do we need to oxidize alcohols? It should be stuck in your mind. You gotta know it. So what's the color change that we see? What's the color change that we see and what do we need? What's the color change we see and what do we need? Just gonna make sure all the stream is still good. Looks like we're all good. I will try to do module 6 as well today. And we're gonna finish module 6 tomorrow morning. Then do some NMR. Orange to green, OMG, orange makes green, exactly that. Yeah, acidified potassium dichromate, orange to green. Okay. So another key thing I want to say, guys, alcohols are soluble in water because they have that oxygen directly bonded to a hydrogen. So we're going to form those hydrogen bonds with our water molecules. Okay. Remember, like dissolves like. Polar dissolves polar, non-polar or not polar dissolves non-polar. Another key thing, guys. Shorter chain alcohols are more soluble in water because the OH group forms a greater proportion of the molecule. The longer chain, the less polar or the less proportion of the molecule that is polar becomes less soluble because like dissolves like. Because water is a polar molecule and we have a polar OH in that alcohol, we want that alcohol to make up more of the molecule. Okay? So shorter chain alcohols are more soluble in water. It's a good thing to know. I think teachers don't really put too much emphasis on that. Depends who your teacher is. So exactly that, guys. Polar solvents dissolve polar solutes and non-polar solvents dissolve non-polar solutes. As we established at the start of the stream, alcohols will have a higher boiling point because of those hydrogen bonding between molecules. Also, just mentioning, guys, we can have primary, secondary, and tertiary alcohols. We need to know this for the oxidation. Primary, there we go. Primary, that carbon that's bonded to the oxygen on the alcohol functional group will only be bonded to one other carbon. Secondary, be 2, and tertiary, 3. Remember, guys, we can oxidize primary and secondary, but we can't oxidize tertiary because we need to get rid of a hydrogen on the adjacent carbon of the oxygen. Because we have 3 carbons bonded to this carbon, there won't be any adjacent hydrogen to remove. So we're not going to be able to oxidize the tertiary alcohol. Right, so oxidizing alcohols, guys, as you've already said, we need acidified potassium dichromate, and we show this oxidizing agent as just an O in square brackets in our equation, okay? And each oxidization, we use 1 O, okay? So when we oxidize that primary alcohol, first we go to an aldehyde, then we go to a carboxylic acid. So we're going to need 2 of these. And remember, we only have water as a product when the alcohol is involved. So if we're going from an aldehyde to a carboxylic acid, there'll be no water in that reaction alone. It's only when we start with the alcohol, okay? So we see the orange to green color change, guys. First, thinking about oxidizing primary alcohols. With an aldehyde, we distill it. With a carboxylic acid, we reflux. Remember, with distillation, we're going to cool and immediately collect. Cool, condense, immediately collect. With a carboxylic acid, we're going to cool, condense, and then let it re-go into that reaction vessel. So just going over the 2, these are the drawings that you need to know for your exam, guys. You need to know the distillation apparatus and the reflux apparatus. So with distillation, we heat the substance, and the products are cooled, condensed, and collected, immediately coming out. Remember that bulb with the thermometer needs to be exactly here. So we want the boiling point to be perfect so we can collect our desired product. Remember with the condenser, the water goes in at the bottom and out at the top. It fills up from the bottom. We need a round bottom flask or a pear-shaped flask. Either one is fine. Then we have that conical flask that we're connecting in, sorry. I think you could also use a beaker, but to be safe, I always use conical flask, and that was fine for me. Then we have our condenser and heat. Guys, why do we not want to use, let me make sure I've written it down. Why do we not use a Bunsen burner? Why do we not want to use a Bunsen burner? Because you need that open system as well. We cannot have that build-up of pressure, okay? So this is used for the primary alcohol to go to an aldehyde, and also we tend to use it for redistillation. Because we need to have that open system so we don't have the build-up of pressure, which would cause our glassware to crack. Okay, it has to be an open system. Too volatile, yeah, you're exactly that, exactly that. Your alcohol could catch fire. So there's two key things why we would use or why we wouldn't use a Bunsen burner. Alcohol could catch fire, which is always scary, and also it's very difficult, sorry, um to control the temperature. That's why we normally use a heating mantle or a water bath. Because you need an open system, open system. Then for reflux, sorry, is continuous heating and reheating. Once again, also an open system, so we don't blow up. Yeah, we have that condenser, water in from the bottom, water out at the top. We have a round bottom or pear-shaped flask. Then we have heat. Once again, we'll use a heating mantle or a water bath. All the vapor is cooled and condensed and returned to the reaction vessel for further reaction. These are the two that you need to know for your exam, guys. You have to be able to draw these two out exactly like this. No open system, the whole thing blows up. So guys, I've even actually got it slightly bigger here. We heat and the vapors are condensed, cooled immediately. Redistillation to purify an organic product. We use a water bath or the heating mantle to regulate the temperature, and the Bunsen burner might set alcohol on fire, or might set fire to the alcohol. Once again, we have an open system to avoid pressure buildup and break up our glassware. Same thing with reflux, guys. Also, anti-bumping granules are used to prevent vigorous and uneven boiling. So this is just recapping what we just saw, guys. We need to know these two. Need to know these two for the exam. So once again, oxidizing our primary alcohols. If we distill it, we go to an aldehyde. Here's the reaction equation. There should actually be plus water here, guys. That's poor from me. Should be plus water. So we have ethanol plus one single oxidizing agent, that O, goes to ethanol. And the ethanol, because it has to oxidize twice, we go first to aldehyde, then carboxylic acid. And then we're going to form like ethanoic acid in this case from ethanol and water. I'm going to try to get one note up quickly. I'm just going to leave my notes for a second. So refluxing a secondary alcohol, guys. We get a ketone. Just give me just a second, guys. Okay. So refluxing that secondary alcohol. By the way, guys, for distillation, I saw some people in the chat. Just wanted to check it in the spec right now. You need a partially open system, just so it doesn't blow up. The glassware will crack. And I do know many tutors have also said you need a partially open system, so I would check that. I definitely check that. But I know in reality, in the lab, it needs to be partially open. Otherwise, there is a risk of glassware cracking. How many oxygens are needed for the oxidizing agent? It depends how many steps you do. Yeah. So in primary alcohol, if we want to go aldehyde and then carboxylic acid, that's two steps. So you're going to need two times the oxidizing agent. We only have one water, however, because we only produce that water when an alcohol group is involved. So going from that alcohol to the aldehyde, we're going to produce water. Then going from the aldehyde to the carboxylic acid, we're not going to produce it. Sorry, yeah, we're not going to produce any water. So we only have one water. We need two oxidizing agents. So refluxing that secondary alcohol, because an alcohol is involved, we are going to have that product of water. Only a single oxidizing agent, and I'm going to form, in this case, cyclohexanone. This is just one example of a secondary alcohol. So oxidizing the aldehyde, it will be under reflux. We start with, I put ethanal here, just some aldehyde, one single oxidizing agent because it's one step going from the aldehyde to the carboxylic acid, no water because we had no alcohol at the start. Okay? And as we mentioned already before, tertiary alcohols do not oxidize because as we know, to oxidize an alcohol, you have to remove a hydrogen atom from the carbon the OH is bonded to, alongside the H from our OH. Because we're forming that water, we get rid of that OH, and we also get rid of hydrogen that the OH was bonded to from the carbon. Okay? So because there is no hydrogen, tertiary alcohols will not oxidize. Guys, it's OCRA by the way, so there may be some. If I say something that doesn't sound like your example, there might be a little bit of a. This is OCRA chemistry, OCRA. When we react to alcohol, we always have water as a product. Good thing to remember, guys. So now looking at the elimination from water, we're going from an alcohol to an alkene. All we need for this, guys, is an acid catalyst and heat. This can be sulfuric or phosphoric acid. So we take the hydroxide from, or the OH from the carbon and the hydrogen from the adjacent carbon. That's how we go from an alcohol to an alkene. Take the OH, take a hydrogen from the adjacent carbon. From here, we can have EZ isomers, guys. We have to be very, very careful with these. I gave the example of butan 2-ol. We can have that double bond either on this first bond or on the second one. If it's on this first bond, we don't have to worry about EZ isomers because looking at this carbon on the left here, or yeah, on the left, we can see that it's attached to two hydrogens. Remember, for that EZ isomerism or isomerism, we're going to need two bonding groups or two different groups, each of the carbons involved in that carbon-carbon double bond. Okay? So we're going to form H2O when we have alcohol to an alkene. And also, if it's on that second one here, we can either have E or Z isomers. It's going to be E when they're on opposite sides. So here our CH3 are on opposite sides. Those are the highest priority groups. Or Z if those CH3 were on the same sides of that carbon-carbon double bond. And naturally, once again, we're going to be forming water. Good thing to remember, guys. They're going from an alcohol to a haloalkane. Is everyone good? Everyone good? Okay. Okay. So going from an alcohol to an haloalkane, we need a sodium halide. This can be sodium chloride, sodium bromide, whatever product you're trying to make, and sulfuric acid. The reason we need sulfuric acid is to produce these H pluses in order to get that water as a product. Because we're removing that OH, we're going to need the H pluses to surround it in order to get H2O as a product. So we have a H plus, we have that chloride ion from the sodium halide. This reacts, bit of nucleophilic substitution, get rid of the OH. This chloride has that lone pair of electrons, will attack that positive or partially positive carbon, depends which mechanism you do, and we have water as a product. So guys, the reactants here would be butan 2-ol, our H plus, and our chloride ion. The reagents, so everything involved, would be that sodium chloride, in this specific case we're using chlorine, our H2SO4, the acid, and the butan 2-ol. So that's the difference between the reactants and reagents. There is a little bit of confusion between the two. The secondary alcohols do not always form three isomers. For example, if the OH, if it was butan 1-ol, then we can only have that double bond on that first carbon. So then we wouldn't form EZ isomers. Only in this case. You gotta be careful with that. Just kind of evaluate where you can form those double bonds. If you can form them in two places, check if you have two different groups to one of those or to both of those carbon atoms in the carbon-carbon double bond. Okay? Definitely a little bit tricky. You've got to be very careful with that. Sometimes it's best just to draw it out. That's the elimination of water, guys, going from an alcohol to an alkene and an alcohol to a haloalkane. On the topic of haloalkanes, so guys, as many people mentioned before, the strength of the carbon-carbon bond increases as you go up the group because as you go up, there's a larger or greater bond enthalpy. Exactly, you can use a combination of different formulas normally when you're writing out your organic molecules. Sometimes they want it all skeletal, and normally they will specify if they say in skeletal formula, they tend to ask for a bit of a mixture. So to investigate our carbon-halogen bond strength, here's what we're going to do, guys. First, kind of similar to paper one, add that nitric acid to remove any interfering ions, for example, like a carbonate, which also precipitates with silver. That's a very key step, as you know your order of tests. Then we will add silver nitrate, because as we know the colors or the precipitates of silver chloride, silver bromide, and silver iodide, white, cream, yellow. So for example, This would be a certain reaction that we would have with H2O. We would have, in this case, chloromethane plus water goes to that methanol, the chloride ion, and that proton. Our halide ion, which we form, would then react with our silver, and depending which halide ion we had, we then form the different color precipitates, either white, cream, or yellow. Silver chloride, silver bromide, silver iodide. And the key thing that we would spot is this yellow precipitate would form first because that carbon iodine bond is the weakest. Therefore, it will be the fastest reaction because it has the lowest bond entropy of this. I guess the lowest bond entropy. Guys, this is OCR. I'm going to keep saying it. So guys, haloalkane to an alcohol, one of the mechanisms that you have to know for OCR, nucleophilic substitution, guys. We have a haloalkane, we have that hydroxide ion, which acts as a nucleophile, has that lone pair of electrons. Curly arrows show the movements of lone pair of electrons, go from an area of high electron density to an area of low electron density. Remember, with our carbon and our chlorine will be more electronegative, so it's going to be delta negative or partially negative. That carbon will be partially positive. Our lone pair of electrons will attack that partially positive carbon, and we get heterolytic fission. Both of the electrons in that shared pair of electrons go to that chlorine atom. So we form our methanol and the chloride ion. Very simple mechanism. This is probably the easiest mechanism in the course. You got to know it. So very key thing, guys. We have to know the purification of organic liquid, and we have to know the purification of an organic solid. So purification of an organic liquid will normally be after your distillation or your reflux. You guys need to know, for OCR, you need to know the type of reaction. They will ask you whether it's nucleophilic substitution, addition, electrophilic addition. They tend to ask these things. So you do need to. So purification of an organic liquid, guys. Following your reflux and your distillation, add water to the mixture so it gets a bit aqueous. From here, you put your sample in a separating funnel. We shake it so it settles into an aqueous and an organic layer. In the question, they will tend to tell you the density of each of these layers, so you'll know which one is above and which one is below after you shake your separating funnel. So what we want to do is we'll collect our organic layer. As I mentioned here, it's not always on the top or the bottom. You have to check the density information that they give you. So from here, you're going to add your drying agent. For OCR, there's two you can say, either anhydrous magnesium sulfate, MgSO4, or anhydrous calcium chloride, CaCl2. These will bind to any of the water present, leaving you with the organic liquid that you want. Then we have to filter the mixture to remove the drying agent. We want to get rid of whatever we have, magnesium sulfate or the calcium chloride, which has a lot of water bound to it, leaving us just with the organic liquid that we want. So these are the steps we need to know, guys. Separating funnel, shake to settle into layers, collect the specific layer that you want, filter it, remove the drying agent, and then normally you don't have to. I've seen different things in different mark schemes. You redistill the sample to further purify it. So we heat to that specific boiling point and get your desired organic liquid. Then collect the sample. These are the very key points, guys, when purifying an organic liquid. So this is the organic liquid, guys, with the minimum amount of hot solvent that's going to be purifying an organic solid. Okay? Because remember, you have to dissolve your organic solid and then let it cool and crystallize, and then from there we'll go on. That's recrystallization. This is the organic liquid. Okay? We have to know organic liquid and organic solid. Those are the two you need to know. Okay. So that's purification of organic liquid. Does that make sense, guys? Does that make sense? I hope the live stream is helpful and the videos are helpful, guys. If they are, feel free to subscribe. But we're just gonna keep going through all the content. Okay. I'll probably go for another hour, maybe. I'll just see how much we can do. TikTok is glitching up. Looks like we're all good. We're gonna keep going. All good. All good. Can you say anhydrous salt? They normally do want you to reference your drying agent. How much stuff do I have to module 6? Actually, we might be done. We have one more thing to module 6, guys. Because I left purification of organic liquid up just for a second. We have one more key thing I want to go over. This is just some key info, guys, for certain questions, I believe. Okay, I'm going to ask you guys some questions. Which three things do the greenhouse effect depend on? Three things. There's three things that the greenhouse effect depends on. So I'm asking about the specific gases here. What three things about those gases that absorb infrared radiation and the bonds vibrate a bit? What three things affect the greenhouse effect? So three things the greenhouse effect of a gas depends on. Sorry if I'm a bit slow, guys. It's just the chat is very delayed for me. Let me know the three things. The vibration. This is a kind of like a bit of a niche question. These are niche one or two markers that a lot of people might not know. Okay. So three things the greenhouse effect of a gas depends on: its atmospheric concentration, its residence time, how long it stays in the atmosphere, and its ability to absorb infrared radiation. These are the three things. This is OCRA, guys. OCRA. Yo, Pax is back. Pax is back. It's good to hear. Yeah, guys. This was not. This was one thing that was really not taught well for me as well in my A levels. This is a key thing to know. These are the three things that affect. Three things the greenhouse effect of a gas depends on: residence time, ability to absorb infrared, atmospheric concentration. Another key one marker in everyday use of infrared spectroscopy breathalyzers, guys. These are just key one markers, little bits of information that they tend to not emphasize in the classroom. Then we have the problems of combusting polymers, guys. Problems of combusting polymers. This can lead to toxic fumes. These are good two, three markers that a lot of people could just be a one mark at the end of the question. Can lead to toxic fumes. Key little things to remember. Oh, these is the breathalyzer thing no longer in the spec? I'm pretty sure it is. I thought I checked. Thought I checked today. So what limits biodegradable plastics, guys? Is not having the right conditions to decompose. In other words, moisture and oxygen. These things might not feel like they're in spec, but they tend to be like one or two markers that tend to be at the bottom. I will just say that. Then what is cracking, guys? We're converting long chain hydrocarbons to smaller ones. So we hit a high MR alkane, we'll go to a small MR alkane plus an alkene. Other key things to remember. Yeah, okay, breathalyzers is. Yeah, I thought so, I thought so. I'm pretty, all this stuff is still in the spec, I'm pretty sure. Another thing, guys, the key definition they tend to ask you, what is a homologous series? It's a family of compounds with the same functional group, with each successive member differing by CH2. So guys, these are just like one, two, three markers. Key bits of information that a lot of people may not have been taught or may not have learned. That I remember, I think I used certain flashcards for these, and I was able to pick up a few marks. Yeah, exactly that. Okay, guys, we are going to be moving on to module six. I may not finish module six today, but we're just going to get through as much as possible. Module six, guys, the one everyone wants and needs. We're going to start with calculate and the delocalized model of benzene. Okay. So what did Kekulé suggest? Kekulé suggested three localized pi bonds. So we have these alternating double bonds. That's what he suggested. Then moving on. Then the model of the delocalized pi bonds and delocalized pi system was developed. You can kind of say pi system, ring of delocalized electrons, delocalized pi bonds, delocalized ring of electrons. All these things tend to be acceptable in mark schemes. So what is wrong with Kekulé's benzene? There are three things that are wrong with Kekulé's benzene. Three things, guys. So we have that the carbon-carbon bonds are shorter than carbon-carbon single bonds, but this would mean benzene would be deformed. This was not the case. When they measured the bond length, they were all the same bond length, had the regular hexagonal shape. The other weird thing about benzene compared to Kekulé's model was it didn't react with halogens. If we have these carbon-carbon double bonds, we would expect them to decolorize bromine water. This did not happen with benzene. So it doesn't react with halogens. If it had the carbon-carbon double bonds, it would react rapidly with bromine. But by electrophilic addition, may I say, because you've got to know that mechanism, it doesn't because the electron density is too low. It's spread out in that delocalized ring of electrons. It requires a catalyst. As we know, it requires aluminium trichloride or tribromide, whatever the halogen is. You can also use iron trichloride, depends what you're using. So it requires a catalyst and does so by electrophilic substitution. We don't see addition, we see substitution. And the third thing was the enthalpy change of hydrogenation was less exothermic than expected. So because benzene is more stable than Kekule's prediction, for cyclohexene, for each of those carbon-carbon double bonds, it would be 120 kilojoules per mole. However, in reality, it was less. It would be 3 times 120, sorry, so it would be 360. We would expect 360 with Kekule's model. In reality, it was less. We saw it to be minus 208 kilojoules per mole. It's more exothermic. So as we know, exothermic reaction, more energy is released bond making than energy to break the bonds. But if it's less exothermic, this means we needed more energy to break the bonds in benzene. Therefore, benzene was more stable, so it couldn't have just been 3 carbon-carbon double bonds. Hope that makes sense, guys. I hope that makes sense. Ooh. So I'm lagging a little bit. So exactly that, we needed more energy to break the bonds. So in reality, it was minus 208 kilojoules per mole, even though, according to Kekule, we predicted minus 360 kilojoules per mole. So it's the three things that were wrong. They tend to ask this, guys. They do tend to ask this. The three things that disproved Kekule's model for benzene. Then for benzene, guys, my best attempt at drawing it, because we have those, we still have the sideways overlap of p orbitals above and below the carbon plane. Very important. Same idea. The bonding regions are above and below the carbons, not in between the two bonded atoms. Same idea. But then we have that delocalized pi bond ring. I think I should say pi ring of electrons. Exactly, benzene was more stable. Exactly, it required more energy to break those bonds. So we had a less exothermic enthalpy of hydrogenation, disproving Kekule's model. And this is just a diagram of what benzene is, those sideways overlap of p orbitals, so we get that delocalized pi system. Okay? So exactly that, guys, the electron density is spread above and below the carbon plane. That's why we have to go through electrophilic substitution and not electrophilic addition. Let me try this, okay? So we have 6 carbons, low electron spread over the 6 carbons, so we have that low electron density. We're unable to polarize molecules, that's why we don't have that addition, and the reactions require catalysts, specifically the halogen carrier. Hope that makes sense, guys. I hope that makes sense. Okay, continuing on. I'm not sure why we just put this here, guys. This feels a bit out of nowhere. Oh yeah, I forgot to put the reduction of nitrobenzene. I decided just to put this one here. The reduction of nitrobenzene, guys. We need tin and concentrated HCl. We're going to need 6 of our reducing agents. The reason is you can simply count the number of hydrogens. Going from NO2 to NH2 and 2H2O, we're going to need 2 hydrogens to form that NH2. And then because we're getting rid of 2 oxygens and we're forming water molecules, if in doubt, a product will be water. If in other doubt, if it's an acyl chloride, we're normally going to have that white steamy HCl gas if it's an acyl chloride. So in these reactions, if you forget a certain product and you can't balance, I would definitely recommend looking at water, or if it's acyl chloride, HCl. So we have 6 H's because we're going to need 2 H's on that nitrogen and then a further 4 H's to make up for that 2 oxygens lost in order to make that product of water. That's a reduction of nitrobenzene. So from here, guys, I got the 2 very key reactions of benzene. So as you can see, the subheading is quite a lot of stuff, just generally benzene reactions. We have Friedel-Crafts alkylation and Friedel-Crafts acylation. So Friedel-Crafts alkylation, we're going to need a haloalkane and a halogen carrier catalyst. As we said before, benzene is stable, so we need to form an electrophile. And once again, both alkylation and acylation are under reflux. So one very key thing, guys, with your halogen carrier and the haloalkane you have is make sure your halogens match. Okay, that's very important. So we start off with benzene. Here we have 1, 2, 3, bromine in the second position, 2-bromopropane. We have our aluminium tribromide. The live is recorded, the live will be on YouTube. We have aluminium tribromide. We reflux it. It could be iron tribromide, but the key thing is we have that 3 bromines. Then from here, we would form the electrophile because we're going to have that AlBl4 minus. But we're going to get there in a second. And we would just be left with a positive charge here. So we form, to get rid of that Br, we also get rid of a hydrogen that's currently attached to this carbon on our benzene to form HBr. And then literally just connecting off because we'd have the positively charged carbon here. We'd connect to that carbon from the benzene and we'd get our final product. You can always go back on a live, guys. You can always go back on a live. If you click under the live, then it will be on my YouTube channel. So forming an electrophile, guys, we would have our 2-bromo-propane plus our aluminium tribromide. We would form that electrophile that we need, and we would have our AlBl4 minus. Okay, so we get that positive charge and that negative charge, and now we have that electrophile that we need for the reaction. So going through the mechanism, guys, we go curly arrow from that delocalized ring of electrons in our benzene to that electrophile, so to that positive charge from the delocalized ring of electrons on the benzene. Then from there, we form this horseshoe. Be very, very careful when forming this horseshoe. It has to be on that carbon. Let me zoom in even more. It has to be pointing towards that carbon. We're about to break this hydrogen bond heterolytically. Okay, very, very cool, very important. We have to be very, very careful with this horseshoe. But then from here, guys, there's horrible writings, by the way. Yeah. Why am I drawing a skeletal? You've got to be doing skeletal, guys. You've got to be doing skeletal. Especially for benzene. So we're going to be forming this, and then because of that heterolytic fission, both of those pairs of electrons, so we break the covalent bond with both pairs of electrons going back into that broken ring. So we reform that delocalized ring of electrons. We have a final product, and we have positive proton, H+. Then we have to reform our catalyst, because remember, guys, the halogen carrier is a catalyst, so we're going to have to reform this. So we have our H+, plus the AlBl4 minus that we used to, once again, guys, make that electrophile. So the H+, plus the AlBl4 minus, we'll get back our aluminium bromide, tribromide, sorry, and our HBr. Now focusing on acylation, guys. For acylation, we're going to need an acyl chloride and the halogen carrier. This is electrophilic substitution, guys. We form that electrophile. We know benzene is too stable for electrophilic addition. Therefore, we have electrophilic substitution. So through the cross acylation, very, very similar idea, guys. We need a halogen carrier. We need reflux. I mean, everything's the same. Everything's the exact same. The key thing is we need iron trichloride or aluminium trichloride because we have that Cl on our acyl chloride. Match up your halogens, guys. Match up your halogens. So we're forming phenyl ketones. So we have our benzene to start off with. Reacting with the acyl chloride. This R is just an alkyl group. We go through iron trichloride or aluminium trichloride. We form our phenyl ketone and we have HCl. That's the overall equation. Now let's go step by step. Forming that electrophile. Same idea as before. We have that acyl chloride. We react it with our iron trichloride. Then we form that positive electrophile. So we get rid of that chlorine. And we form FeCl4 minus. Remember, we are going to have to reform our halogen because it is a catalyst. If it lets me go down, guys, okay, here we go. Mechanism, exact same thing as before. We have that curly arrow going from that delocalized ring of electrons in our benzene to that positive carbon. Same thing as before, guys. We have that horseshoe now, that broken ring of electrons. Then we have a curly arrow breaking this bond heterolytically with both electrons and the pair of electrons going back in to rebuild the ring, essentially, reform the ring. Yeah, because once again, this carbon cannot have. Well, in this case, you can't. In this case, you could think about having, alternating double bonds. There's one too many bonds, so we break this bond heterolytically. Curly arrow going back into our horseshoe. So we form our phenyl ketone and that positive hydrogen that we lost because this bond broke heterolytically, with both electrons going to reform that delocalized ring of electrons. This is electrophilic substitution. Electrophilic substitution. Why is it electrophilic substitution? Because we have an electrophile. Electrophile and electron pair acceptor. It's positively charged. It wants some electrons to lose that positive charge. Electrophilic substitution. Benzene is too stable for electrophilic addition. So to reform that catalyst, we have our iron FeCl4 minus added to that H+. We reform that halogen carrier, FeCl3, and we get hydrogen chloride. Okay? Because we have a H+ reacting with one of these chlorines. It takes off that chlorine to reform the halogen carrier. Exactly. Electron pair acceptor, it's an electrophile, and we know benzene can't undergo electrophilic addition. So guys, Friedel-Crafts alkylation and acylation, they're both under reflux. They both require a halogen carrier. And we both have to reform that catalyst at the end. Okay? Nothing crazy. Nothing crazy at all. Because we still got loads to go through, so let's keep going. So I believe, yeah, nitration of benzene, guys. Another key reaction you have to know. Less than 55 degrees if you want mono nitration. We perform it in a water bath to control the temperature, and the reaction is exothermic. Another reason why we want that controlled temperature. So conditions and reactants, I just said 50 degrees as long as it's less than 55. 50, 45 tends to be a good temperature. We need concentrated nitric acid and a concentrated H2SO4 catalyst. I know a lot of people like the nitration of benzene. People like forming that electrophile of NO2 plus. Let's continue. So the overall equation, we have our benzene, we add the nitric acid, form nitrobenzene, we have our water. Okay, nothing crazy at all. To form the electrophile, so a lot of people do this in one step. Me personally, I prefer to do 2 steps because I think it makes a little bit more sense, but you can do it one step, it might just be easier and quicker in the exam. We have our sulfuric acid and our nitric acid. Our sulfuric acid will lose a proton, so we'll have HSO4 minus. Our nitric acid will gain a proton, so we'll have H2NO3 plus. This forms the electrophile. Then from here, our H2NO3 plus, we're going to get H2O and NO2 plus. This NO2 plus, exactly what we need. That's our electrophile. And then as I wrote here, the overall here, or you could just write in the exams to speed things up, will be your nitric acid plus your sulfuric acid goes to HSO4 minus. It's going to have to be reformed because it's a sulfuric acid catalyst plus H2O, bit of water, and our NO2 plus. Now we have our mechanism. Same idea as before, guys. Benzene electrophilic substitution. Same idea with the mechanism. We have that curly arrow showing the movement from areas of high electron density to low electron density of that lone pair of electrons. It attacks our electrophile, so it's susceptible to electrophilic attack now that we have the electrophile. The same idea before, we form that horseshoe, make sure it's pointing to the relevant carbon. It's going to be positive charged. Can you share your notes? Drop a link in bio. Oh, sorry, yeah, I will after. I will after this. You're going to have all the notes. Yeah, I will share all these notes, guys. Sorry. You do not need to know both steps, guys. You can just write out this for forming your electrophile. So then in the mechanism, heterolytically break this bond, both of those shared pairs of electrons going back into reform this delocalized ring electrons. From here, we're left with nitrobenzene that we need, plus that positive proton. Nothing crazy, guys, nothing crazy. So that's your mechanism. The mechanism is consistent of all of these electrophilic substitution reactions. They're all the same. You just need to know how to form your electrophile depending on what you're trying to do with your benzene. Nitration of benzene is a very common 6 marker. We'll see if it comes up. To reform the catalyst, because we currently have that positive proton, what was the catalyst? Go back up. It was that sulfuric acid. Where that concentrated sulfuric acid catalyst. So reform the catalyst, we have that positive, we have H plus, add it to our HSO4 minus, that gives us exactly what we need of H2SO4. That's sulfuric acid catalyst reformed. So continuing on now, guys, just going through all the reactions of benzene. Halogenation would be the same idea to form that electrophile. We do need to know the mechanism for all of these as well, guys. But we'd have our benzene plus chlorine using that halogen carrier of AlCl3 or iron Cl3, as long as you have that chlorine. We get our chlorobenzene and HCl. Same idea as before. Forming that electrophile, we have our AlCl3 plus the chlorine. Same thing as before, guys. We then get that chlorine, sorry, Cl plus, the electrophile, and AlCl4 minus. Going through the mechanism, guys, exact same thing. Curly arrow from the delocalized ring of electrons to that Cl plus. Same thing, horseshoe in the direction of the relevant carbon. Make sure you're not making it ambiguous, so it is really pointing to the relevant carbon. So then we have our chlorobenzene and we have that proton. Once again, we need to reform that catalyst. What are we trying to reform? We're trying to reform our aluminium trichloride. We need this AlCl4 minus to become our aluminium trichloride. So reforming the catalyst, because we're left with this H plus, we're gonna have our H plus the aluminium, plus the AlCl4 minus. It's not letting me scroll down. Plus the AlCl4 minus, going to reform that halogen carrier plus HCl. Nothing scary here, guys. Just reforming the catalyst. We know we need to do this, and we aren't going to be left with this H plus floating around in these substitution reactions. Now moving on to directing effects, guys. OH and NH2 are 2,4,6 directing or 2,4 directing. Why? Because the electrons partially delocalize into the ring, increasing the electron density of the ring at carbon 2, 4, and 6. So these carbons are more likely to react. Okay? So also a key idea, why is phenol more reactive? Because the lone pair of electrons on the oxygen partially delocalized into the delocalized ring or into the pi system, increasing electron density, making it more susceptible to electrophilic attack. And then a good way to think of it, so these are the 2,4 directing groups or 2,4,6 directing groups. The ones that aren't, so these increase the electron density, they partially delocalize into electron donating groups. Yeah? The way to think of the one that's not is NO2? No. Is electron withdrawing? No. NO2. It's good to remember. No, for example. That's what my teacher used to tell me, and it did help to be fair. We have no electron delocalization. It withdraws density from the ring. It's an electron withdrawing group. It's 3,5 directing. So carbons 3 and 5 are more likely to react. So with the OH and the NH2, these partially delocalize into the ring, and 2,4,6 increase in electron density, making them more likely, more susceptible to electrophilic attack. NO2 was 3,5 directing, will withdraw that electron density, therefore carbons 3 and 5, the opposite, were more likely to react. So these are electron donating, because it's delocalizing into the ring, and NO2, electron withdrawing. Kind of makes sense because this is increasing the density, whereas this is taking away the density. I'm lagging a lot. Guys, give me a thumbs up. Like my laptop's not burning. Give me a thumbs up if you can hear me, guys. I'm not going to continue until I get some thumbs up because I'm a little bit unsure. I don't want to be talking if it's not working. Thumbs up if it's working. Thumbs up if it's working. If not, let me know. Damn. Okay, good. There was just a whole ring. Looks like people are happy. Looks like people are happy. Guys, let me know if this is useful. Are my explanations okay? Is everything all right? Let me know. I'm gonna carry on though. Let me know if it's not useful. Let me know if it's not useful. Okay. So from here, because we know NO2 is 3,5 directing, if we react it with chlorine, with our halogen carrier, it's going to go to either carbon 3, or I guess if there were two of them, it would be 3 and 5. If there were one of them, it would always be carbon 3, wouldn't it? Plus HCl. Why HCl? Because we get left with one chlorine here, and we remove the hydrogen from the carbon that we're bonding to. Okay, cool. I'm happy that it's useful. Okay. Module 6 is definitely more important. Then with our phenol guys, that OH group is 2,4,6 directed because the electrons partially delocalize into that delocalized ring of electrons or pi system, whatever you want to say. Increases electron density, more susceptible to electrophilic attack. Carbons 2, 4, and 6 increase in electron density. So we have that chlorine electrophilic substitution on the second, for example, the second carbon. And we form HCl, or it can be 4. Now, two things I wanted to address, guys, with phenol, with dilute nitric acid, and phenol with concentrated nitric acid. If we react it with dilute nitric acid, okay, if we dilute nitric, sorry guys, I was just reading the chat. We're gonna get mono substitution. OH once again 2,4,6 directing, second carbon plus H2O. Why is it H2O? Well, we already saw before. If I will go up very quickly, guys, to the nitration of benzene. We have H2O as that product when we form our electrophile. We've got the HSO4 minus, the H2O, and the NO2 plus. So we have that water as a product with the nitration of benzene. Good to know. Good to know. However, when we're in concentrated nitric acid, we have our phenol plus 3 HNO3. And then we get a tri-substitution at carbons 2, 4, and 6. This guy wants spit ion so much. Sorry, guys. And then we're going to form 3 H2O, because on each single one of these, get rid of that hydrogen, and we have 3 NO3. So it's just 3 H2O opposed to 1. Nothing scary there. Right, guys, going over phenol. I love phenol, guys. I'm a fan of phenol. I do prefer module 6. I feel like my explanations are better for module 6. But yeah. So phenol, uses of phenol, antiseptics, dyes, and detergents. If they ask you use of phenol, they normally just be one, but you gotta name one of these. Antiseptics, dyes, and detergents. So why is phenol more reactive than benzene? We know this already. That lone pair of the oxygen on the oxygen partially delocalizes into that pi ring. Electron density increases in the ring of phenol. The ring is now more polarizing or more susceptible to electrophilic attack. You can say either one. And once again, remember we are inducing dipoles to make molecules polar. Okay, so that's why phenol is more reactive than benzene. Very key piece of information. Phenol is a weak acid. Phenol is a weak acid. It reacts with strong bases, like sodium hydroxide, and metals. However, it does not react with weak bases. We know we can differentiate between phenol and a carboxylic acid because phenol will not react with sodium carbonate, whereas a carboxylic acid will. So carboxylic acid will form CO2 in that reaction. So if we see effervescence and we're differentiating between phenol and a carboxylic acid, we will see effervescence with sodium carbonate for carboxylic acid. We won't see any reaction for phenol. Exactly that. So if we have our phenol plus sodium hydroxide, we get this sodium phenoxide in this case, and H2O. Nothing scary, guys, nothing scary. H2O because we lose that hydrogen on the OH, and we get left with this hydroxide ion, so we form water. So exactly as I said already, guys, we can use this fact that it's a weak acid to distinguish phenol from a carboxylic acid. Carboxylic acids will react with sodium carbonate, with our products being H2O, CO2, and a salt. This is simply just acid plus metal carbonate. We know forms water, CO2, and a salt. So we're going to see effervescence. That's how we differentiate between the two. Next important thing, guys, phenol reacts readily at room temperature with bromine. This forms a white precipitate. So we have our phenol. Oh, lagging a bit. Okay, so we have our phenol with 3 bromines on it. So how do we get this? Our phenol with 3 Br2. We get that bromine once again 2,4,6 directed. Carbon 2, carbon 4, carbon 6. Then each time we're going to lose a hydrogen, as we saw in the mechanisms, or with all of our mechanisms for electrophilic substitution. So we get 3 HBr. No halogen carrier is needed, guys. No halogen carrier is needed. And we're forming a white precipitate. These are 2 key little ideas that we should know for phenol reacting readily at room temperature with bromine. So acyl chlorides, guys, moving on to acyl chlorides. I know we all love acyl chlorides. Give me a thumbs up if you love acyl chlorides. Or subscribe and hit the like button if you love acyl chlorides. So here we have propanol chloride. This is the example I'm going to be using in these reactions. So we need to know the different reactions of our acyl chlorides. So acyl chloride going to a carboxylic acid. How do we do this, guys? Know your reaction pathways. This is water. Carboxylic acid to an acyl chloride is SOCl2. Acyl chloride to a carboxylic acid, we need water. So we have our propanol chloride plus water. Remember, guys, with acyl chlorides, we tend to get that white steamy gas, HCl, as one of our products. Okay, people do not like acyl chlorides. So we have a propanol chloride. Remember, we name it like that, guys. It'll be propanoil, ethanoil, whatever it is, and then the chloride for our acyl chloride group. So reacting it with water to get from an acyl chloride to a carboxylic acid, we form our carboxylic acid. What do we lose? We lose that chlorine. And what do we have left? Well, we lose this OH for the carboxylic acid. So we're just going to be left with a hydrogen, and the chlorine is going to form HCl. Then going from a carboxylic acid to an acyl chloride, we need SOCl2. So remember, guys, on your reaction pathways for OCRA, they're kind of like at the bottom, they tend to be small arrows as well. 2 very important ones. So carboxylic acid to an acyl chloride, we have our carboxylic acid, SOCl2. Guys, it's very good to think about your products and then what you can make from it, sorry. So we're going to need that 1Cl going here to form that acyl chloride. What do we have left? Well, we have O, we have the OH from our carboxylic acid and a single Cl. With acyl chlorides, we tend to get one product to be HCl, As you can see on both of these, we get HCl, and then we have SO2, essentially just collecting what's remaining to get SO2. Yeah, guys, these are aqueous, sorry. These ones are aqueous, just in general, when we have reactions with acyl chlorides, we tend to form those white steamy fumes, HCl gas. The most important thing normally with these acyl chloride reactions, they won't want symbols. So the important thing is just to know that HCl is formed. Aqueous. Aqueous, guys, aqueous. Who said Aquarius? Oh no, that's poor. Guys, acyl chloride to a primary amide, all we need is ammonia. So we have our acyl chloride. Remember, guys, this is quite similar. I guess you kind of think of it as an alcohol plus a carboxylic acid in a certain way. Because that acyl chloride is essentially acting as that carboxylic acid, and that ammonia is essentially acting as that alcohol. It's a weird way to think of it, but it's like forming those esters, but this is forming amides. Or just know your reaction pathways. Acyl chloride to a primary amide, we have our acyl chloride plus two ammonia molecules. We form that primary amide, so we only have one carbon coming off that nitrogen. Then we form ammonium chloride or an ammonium salt, okay? Because what do we have left with? We're left with four hydrogens. We still have a nitrogen, and then we have this chlorine that we lost from the acyl chloride. So another important reaction. There they all are, guys. There they all are. We also have an acyl chloride going to a secondary amide. I assume you guys can imagine what we have to use. Because here we just needed ammonia, we're going to need a primary amine. Just reading things. If you apologize now, I'll be happy. Oh, sorry. Yeah, I'm actually sorry. I'm not trying to call you guys out. Sorry. Just trying to engage with the chat. Like and subscribe if it's helpful. So going from an acyl chloride to a secondary amide, sorry, we use a primary amine. We have our acyl chloride, we have our primary amine. Primary because its nitrogen is bonded to one carbon atom. Then from here, we form that amide. Secondary amide because this nitrogen is bonded to two carbons. We're bonded to two carbons plus HCl. As we know, with our acyl chlorides, one of our products tend to be HCl. So if you get stuck in an exam, just guess. We can also see, what do we lose? We lose this chlorine, and we lose a hydrogen. Right, continuing on, guys. We're going to move on to esters, I believe. So we did a bit on amides here. Moving on to esters. So we're going to use propyl ethanoate. I just wanted to show this as an example, guys. Remember, the ill part, the ill part of your naming will be responding to that single oxygen. Can I explain quickly how to name? Which one do you... Oh, yeah, the ester, for sure. We're going to be going over amine naming as well. Everything will be covered. So with what's bonded to the single oxygen, we form the alkyl part of the name. So here, how many carbons do we have? 1, 2, 3. It's going to be propyl. And then the bit that's bonded to the carbon, which is then double bonded to the oxygen. Count the carbons. 1, 2. It's going to be ethanoate. So we have propyl ethanoate. And that's how you name esters. The ill part is bonded to the single oxygen, and the O8 part is bonded, or part of the carbon that's bonded to the double oxygen. Oh, yeah, sorry, guys. Sorry, yeah, I'll explain the amide thing. Okay, yeah. So this secondary amide, same idea as our esters, okay? This part will be the ill part, okay? And because it's bonded to this nitrogen, it's going to be N-ethyl. But for example, guys, if you had, I'm trying to think of a good example here. I can't really think of another good example. But the bit that's on this like shorter chain, the same thing that's bonded single to the oxygen will be N, then ethyl, propyl, whatever it is, okay? Oh, okay, wait, I have another example, guys. So if this nitrogen had, let's say, instead of this hydrogen, it was a tertiary amide, so we had another chain coming off it, you could simply call this N-ethyl, N-propyl, and then in this case, because we have 1, 2, 3, it'll be propanamide or propanamide. So this is a key thing to know, guys. It's quite rare in the exams, but this shorter chain, or not shorter chain, the bit that's bonded to the nitrogen, this comparing it to a single bonded to the oxygen, is that N, then ethyl, If we had two chains, it would be N-ethyl, N-propyl, for example, and then we would have this propanamide. Propan because they have one, two, three, and they're single bonded to the carbon. My phone is very low on charge, guys. Just gonna quickly put a charger. Maybe I can change the. Gonna have to end the TikTok live. I assume most people are here. Sorry, guys, just ending the TikTok live. Putting it charging. Might put it back on if we go on for much longer. Good thing to name amides. You won't get one more complicated than this because it's not something they focus on too much in the spec. So continuing on to esters, guys, we already went over the ester naming. Now synthesizing esters, big words. We have a carboxylic acid and an alcohol under heat and concentrated sulfuric acid. So in this example, 1, 2, 3, we have propanol, propan 1O, and we have 1, 2, ethanoic acid. So we're going to form exactly that, guys, because we had that propanol. We've got that 1, 2, 3, so that'll be propyl, ethanoate, and water. Why do we get water? Why do we get water, guys? I want you guys to tell me, do we lose, the OH from the alcohol, or do we lose the OH from the carboxylic acid? So where do we lose this full OH? Is it from the carboxylic acid, or do we lose it from the alcohol? Let me know, guys. Where does it lose from? So we're forming this water. Is it from the alcohol, or is it from the carboxylic acid? Let's see what people are saying. I'm seeing lose it from the carboxylic acid, from acid, carboxylic acid, acid, carboxylic acid, acid. Exactly that, guys. Exactly that. We lose the OH from the carboxylic acid, and we just lose a single hydrogen from our alcohol. It kind of makes sense because you kind of want to leave that one oxygen from the alcohol forming with that essentially carbon bonded to that double bonded oxygen. So we lose the OH from the carboxylic acid and the H from the alcohol. So we get our propylethanoate and water. It's very important, guys, because in these kind of questions, they may ask it something like an acyl chloride and an alcohol or an amine, and then you might have to figure out where you're losing certain things from. I've seen before in a multiple choice question. So continuing on, the other way we can make an ester, guys, is an acid anhydride and an alcohol. We have no need for a catalyst here. If we're going from an alcohol to an ester, we do need that heat and concentrated sulfuric acid. But if we're going from an alcohol with an acid anhydride, there is no need for a catalyst. All right, guys. So I'm just reading the chat for a second. Amide, guys, amide. Oh, you guys are beefing a little bit in the chat. Calm down, calm down. So an acid anhydride, guys, nothing scary, nothing scary. All it is we have both of these carbons, single bonded to an oxygen, so double bonded to another oxygen, and then you're going to have your carbon chains. Okay? Nothing scary at all. Nothing scary at all. Then we add it to our alcohol. In this case, remember, our alcohol was propanol, or propan 1O. So we form our ester bond, and then we form a carboxylic acid. Hope that makes sense. So we're going to lose that hydrogen from the alcohol, and then we're also going to break this acid anhydride bond either here or here. Okay, so it's going to form that carbon single bond oxygen bond, carbon single bonded to the oxygen with our alcohol. I feel like organic chemistry is always hard to articulate, a lot easier just to draw it out. And then we get left with that carboxylic acid because we lose that hydrogen from this alcohol. So we get the two products of the ester and our carboxylic acid. Do you want a 5-minute break? I missed 12 minutes. Guys, what do you want me to go over? Do you want me to go over anything? I'm seeing everyone wanting a 5-minute break. Guys, I'm going to, let's finish this page, and I'm going to ask you guys if there's any one topic that you want me to repeat going over the page of notes. So in this case, this will be ethanoic anhydride, sorry. The reason is 2 carbons here and 2 carbons here. It's ethanoic anhydride. You don't think about the total number of carbons. Look at each side. Okay. No break, lock in. What's the difference between an amide and an amine? So an amide, guys, going back up, amide is this functional group. When we have a nitrogen, single bonded to a carbon, double bonded to an oxygen. An amine would just be that either NH2, could be NH, could be NH, well, it can't be NH3, unless you have ammonium's ions and ammonium salts, then that gets something else. But amine will not have that carbon, adjacent carbon bonded double bonded to an oxygen. Okay, so if we see this N bonded to a carbon, which is then double bonded to an oxygen, this is an amide. Okay, you guys are watching on the toilet. That's all good. We'll carry on then. Okay, so we did this acid anhydride plus the alcohol. Definitely very important to know. No catalyst needed. I just want to say, guys, if this wasn't two carbons on each side, it could be ethanoic, propanoic, anhydride. Okay? So don't be intimidated if you have three carbons on one side and two on the other. Nothing scary. So, guys, acyl chloride plus an alcohol, another way to make an ester, no catalyst required. So, both for the acid anhydride and alcohol, and the acyl chloride and the alcohol, we do not need a catalyst. Whereas if we have an alcohol and a carboxylic acid, we do need that concentrated sulfuric acid catalyst. Okay? So acyl chloride plus an alcohol, sorry, no catalyst needed. This is just ethanol chloride plus propanol. And then we have our ester, which will be propyl ethanoate. And then we have our HCl because what do we get rid of? We get rid of that chlorine. Same thing as before, guys. Whatever's on this part of our carboxylic acid, we remove, and we remove that single hydrogen from our alcohol. So that's H and a Cl, we get HCl product. Guys, I just wanted a little naming practice, but I already showed the name. So how many carbons do we have coming off that single oxygen? Not the double bonded one, just the one that's single bonded to the carbon. 1, 2, 3, propyl. Then focusing, because remember, guys, this is going to be a carbon number one because it has that ester group bonded to it. That is that highest priority functional group. So we have one longest chain, 1, 2, 3, 4. So we're going to have butanoate. Where is that methyl group relative to this first carbon? It's on the second carbon. So this will be propyl 2-methyl butanoate. Pretty common question they could ask. Okay, okay, I'm seeing the chat. Guys, you got to lock in. Paper two is very soon. Not the time for shenanigans, guys. Come on. Okay, so continuing on, guys, that was acyl chlorides and esters. Okay, naming amines, a little bit of phenol and acyl chloride reaction. Okay, so phenol and acyl chloride reaction. So remember, guys, phenol is a weak acid, so it reacts very, very, very slowly with carboxylic acid. So if we want to form this ester bond with a single oxygen to the carbon, double bonded to the other oxygen, we use an acyl chloride. So we have phenol plus an acyl chloride goes to this phenyl ethanoate. Why, guys? Why is it phenyl ethanoate? Because single bonded, so the oxygen that is single bonded to the carbon has our benzene or phenyl group. 1, 2, 2 carbons, ethanoate plus HCl. Why? Because what are we losing? We're losing this hydrogen from the phenol and we're losing this chlorine from our acyl chloride. Gas chromatography and TLC. I have a little bit of information on both of those, not too much. So naming amines, guys, it's nothing scary when naming amines. Very similar to your other functional group naming, but a lot of people get intimidated. So here, longest carbon chain, 1, 2, 3, 4. We have this primary amine here. So it's butane 1-amine. Nothing scary. Same idea, if that amine was on a second carbon of our longest chain, same thing, 4 carbons, it would just be butane 2-amine. Looking at secondary and tertiary amines, same idea as before, guys. The shorter chain would be N-alkyl. The rest will just be the same as that primary amine naming that we just did. So looking here, this nitrogen is bonded to 2 carbons, so it's going to be a secondary amine. So the shorter chain will be this just the CH3. So we have N-methyl. So we just have the CH3 coming off this nitrogen as the shorter alkyl chain, shorter carbon chain. Then what do we have here? We have 1, 2, 3, 1, because it's on that first carbon, propan 1-amine. Nothing scary. And looking at the tertiary, guys, another key thing, shorter chains are these CH3s. So we're going to have NN, dimethyl because it's just two CH3s coming off the N and then the shorter chain. So we have N dimethyl, and then how many do we have? One, two, and our longest carbon chain. So it's going to be one A. Nothing scary there, guys. Nothing scary there. Just making sure that my stream hasn't crashed because my laptop is very laggy. I'm gonna try to get the TikTok live back up, guys. Is there anything you want me to leave up on the screen while I do that? I shall leave this up. I'll leave this up just for a second. Just getting the TikTok live back up. Just give me a second, guys. Just making it available in case people want to watch. Okay. Sorry about this, guys. Sorry about this. Okay, we're back live on TikTok. My phone is charging. So that was the name of the amines, guys. Just gonna read the chat for a second. Pick topic, say topic. Can you go back over between amines currently? Chiral carbons, when we have four groups bonded to a carbon and we see optical isomers forming two non-superimposable mirror images. We're going to be going over that for sure. And then here, guys, when we have two amines, longest carbon chain, 1, 2, 3, 4, we have that butane, 1, 2, because that highest priority group, or sorry, shortest path to that amine group will be on that first carbon. Then we're going to go to the third carbon. So we have butane, longest chain is 4 carbons, 1, 2, diamine. Nothing scary. Okay, continuing on, guys. I believe we have, yep. I'm not even going to write it, I'm not going to show you guys what do we use if we want to identify an aldehyde. What do we use? So if we already identified that is a carbonyl group, what do we use to identify an aldehyde? What do we need? What do we need, guys? What do we need? Okay, someone's spamming a little bit. We're not going to go on for too much longer, guys. Just looking at how many topics we have left. Nothing crazy. Nothing crazy. Tolerance. Exactly, tolerance. Perfect, guys. So how tolerance works? It forms a silver mirror in the presence of an aldehyde. So we test for an aldehyde, and it contains those silver ions. Then we have AgNH3 2 plus in an aqueous solution. It's colorless, and it's made by silver nitrate, sodium hydroxide, and ammonia. Yeah, 2,4-DMP is Brady's. You can say Brady's. The reason it works is because we're using the fact that an aldehyde can easily be oxidized, whereas a ketone cannot. Because the aldehyde can be oxidized, our Ag plus ion will be reduced, forming that silver mirror. So an aldehyde oxidizes to a carboxylic acid. This is what we're using in order for tolerance region to work. The silver mirror forms, the Ag plus is reduced to simply just solid silver, forming that silver mirror. Okay, chiral centers, guys. Looking at chiral centers. So chiral carbons. Chiral carbon is bonded to 2 to 4, different atoms or groups. The very key thing is to check for symmetry. I'm going to go over why. When we have a chiral carbon, this forms two non-superimposable mirror images. So for example, guys, looking at these two organic molecules, we can see, because it's not symmetrical on the left molecule here, we would indeed have two chiral carbons. Because looking at this carbon up here, if you bond it to a hydrogen, this methyl group, then going around the chain, you can see it's not symmetrical. As this one has a chlorine, 1, 2, 2 carbons away, then going around the left side, or anti-clockwise, we would be 1, 2, 3, 4 carbons away from the chlorine. So we have a chiral carbon here, and we'd also have a chiral carbon here. Because going around anti-clockwise, we're 2 away from this methyl group. Then going around clockwise, we're 1, 2, 3, 4 away from the methyl group. And then of course, we're bonded to a hydrogen and a chlorine, 2 chiral carbons. Over here, because it's symmetrical, this carbon will be 1, 2, 3 away from the chlorine, and then going clockwise would also be 1, 2, 3 away from the chlorine. So we will not have chiral carbons here. So now one of those key 1, 2, 3 markers, like those weird questions where they want those extra marks. What is the problem with reducing chiral drugs? The separation of our isomers is very expensive. They can have side effects because of those isomers. The solution, we use a chiral catalyst. You don't need to know too much about that. Key thing is just to know that we use a chiral catalyst and we use chiral synthesis. This is a key little thing for those 1 or 2 markers that can earn you those extra marks. Now, drawing those non-superimposable mirror images, look at the example here. Remember, guys, with chiral carbon, it will be tetrahedral shape because we have that carbon bonded to 4 different atoms or groups. Sorry, guys, my hay fever is killing me. It's not great. So we have those 2 non-superimposable mirror images, and when we have that carbon tetrahedral shape, as we know, we have 2 on the same plane, and they're kind of going in a similar direction, kind of one down, one nearby it. We have one going into the paper and one going out from the paper, shown by the wedged and the dashed lines. So we have that tetrahedral shape, and then we simply draw that dashed line in the middle, and these are images. I apologize for the disgusting handwriting, but that's about it. Yeah, I will be doing an MR, sorry, tomorrow. All right, continuing on, guys. I believe I believe we do have a little bit polyamides, polyamides and polyesters. These are condensation polymers, guys. We're removing water. Okay, we had the addition polymers with our alkenes, but these are condensation polymers. Guys, I think we're gonna go maybe for 5 more minutes. I think I'm gonna leave. Oh, I'm not sure how much to leave. I might just do this one more page and then we're gonna finish the rest tomorrow morning, not for long. And then we're gonna do NMR in the evening. So polyamides and polyesters, condensation polymers, guys. 2 very, very key facts. So we're going to have dicarboxylic acids and diamines to form, in this case, condensation polymer. So we're going to have N diamines, and we're going to have N times dicarboxylic acids. All we have to do, guys, same thing with that ester bond. We have that N. I think this N should have a hydrogen on it, no? Am I going crazy, guys? We lose the OH, and we lose the H. This N should have a hydrogen onto it, I'm pretty sure. Unless I'm going crazy. How long is tomorrow morning? Tomorrow morning won't be long. It will not be long. Because am I going crazy? This N should have a H on it, right? So I've been doing this for a while now. Let me know. I'm already going mad. 10 a.m. tomorrow? No. This is yeah, this is yeah, it should have a H. Yeah, I apologize guys. Wait, I feel like it does, right? Because we would lose that OH here, and then we lose a single H on our amine. Yeah, this should have a H onto it, guys, because we lose that OH from the carboxylic acid. And remember, like the alcohol, we lose that single H. Yeah, exactly. Yeah, nitrogen has 3 bonds. Yeah. I don't know what I was doing here. So these nitrogens should have H's because, as we know, we lose 1 hydrogen from the amine slash alcohol and OH from the carboxylic acid. From here, we're forming 2N minus 1 H2O. Why is it minus 1, guys? So we have 2N H2Os, then we have to take away 1. Why is it minus 1? Why do we have minus 1? It's a very key, important thing. Yeah, both of these should have a hydrogen on them. Is there any way I can like draw onto it? Ah, it's too late now. Okay, well I'm saying it, guys. It should have no hydrogens on them. We only removed 1 hydrogen. There's a poor mistake from myself. Kind of put the answer here because we have that 1 amine and that 1 carboxylic acid at the very end of our long chain polymer. We'd have 1 less H2O. So we're going to have H2O every single time we have this amide bond forming. But then we'd have at the end, because we have 1 carboxylic acid and 1 amine, which would have formed 1 more water, we have to take away 1 water from the total number of waters produced. Now focusing on amino acid, guys, amino acids, and we want to form polymers from there. If we have N amino acids, same idea, guys. This time I had the H on the nitrogen, not sure why I didn't do it before. So we form amide bonds. This is one repeat unit. Same idea as before. We extend those bonds out, have n times, and we form n minus 1 H2O. Because on the ends, we'd have still one amine and one carboxylic acid. So for every time these join, we form a H2O. Because we'd have essentially one water missing out or one bond at the end missing out, we'd have one less water produced. And the other way we can be forming a polyamide can be from a diamine and a diacyl chloride. So let's go over that one more time, guys. Dicarboxylic acids and diamines, amino acids, or diamine and a diacyl chloride. Don't stress too much about this, guys. The key thing is we're forming these amide bonds. So we have n times of this diamine, n times of this diacyl chloride. Don't get scared. All it is that acyl chloride functional group at each end of our organic molecule. So same idea as before, guys. We form that amide bond. And yeah, I have the H's here as well, guys. It must have been poor from me. So from here, same idea as before. We have that amide bond. This is two repeat units. Oh, sorry, this is one repeat unit because we have. Sorry, guys, I was thinking back to the amino acid. One repeat unit. We form the amide bond, and we have that bond extending off with the brackets going over exactly as written out n times. Same idea as before. We have 2n minus 1. This time it will not be H2O because remember, we use this part of our carboxylic acid, so it's going to be a chlorine here, and we lose one hydrogen from our amine. So losing that one hydrogen, losing that chlorine, we have 2n minus 1 HCl. Okay, guys, we are going to stop there. I'm going to finish everything else tomorrow morning. It's going to be a short stream tomorrow morning, and I'm going to be going over any of these topics that anyone wants to tomorrow morning. I'm going to finish there, guys. I'm going to answer any questions now if you have any, and maybe have some fun with one of drawing out some mechanisms while I answer questions, because why not? So I'm just going to draw out some mechanisms as I answer any questions that you guys have. If you have any questions about the content, I will go over it again. What time? 10 a.m. tomorrow morning, it will be recorded. I hope today was useful. I hope it was useful. 10 a.m. tomorrow morning, and then we're going to have, once again, we're going to have NMR and unseen mechanisms in the evening. I have 5 NMR questions already prepared. Can you give us some tips? Organic chemistry is a memory game. Live and breathe organic chemistry until your exam. Stare at that reaction pot. Well, not just stare at it. Do questions. Maybe breadth and depth in chemistry papers. And yeah, I'm just going to be drawing out some of the key mechanisms that you guys need to know if we have any new viewers. Just going to be drawing out as much as I can in this period. And I'll be looking at the question. I'll be looking out for any questions. If you guys want me to re-explain any of the topics that we went through today, let me know. But if not, no worries. I'm not sure why this OneNote isn't. I'm going to quickly refresh it. I'm only doing NMR and unseen mechanism questions, guys. Only NMR and unseen mechanism questions. I'm going to have to use OneNote tomorrow. I apologize in advance, but you know, for NMR, you have to do it. So, guys, I'm just going to be drawing out each of the mechanisms that we've talked about today, just all these curly arrow mechanisms that you need to be knowing for your exam. I'll probably just be doing this for 10 minutes and answering any questions if you guys have any. Tips for maths paper 3. Depends which one you're more comfortable with. If you're more comfortable with mechanics, do more stats. If you're more comfortable with stats, do mechanics. You've got to be focusing on what you're not comfortable on because you want to get as many marks as possible. I assume you're all aiming for the A star. So just going over electrophilic addition, guys. Just going to be drawing out mechanisms while people answer or ask any questions. Remember that area of high electron density, we polarize our bromine molecule. At that carbon-carbon double bond, we get a heterolytic fission between our bromine-bromine bond with both of those shared pairs of electrons going towards our partially negative bromine. 10 a.m. tomorrow morning, guys. 10 a.m. tomorrow morning. Just drawing out all these mechanisms here, guys. So from here, because we don't need to worry about major and minor products because we don't have a more stable carbocation, we form our intermediate, a carbocation intermediate, because we had that curly arrow going to a partially positive bromine, because curly arrows go from areas of high electron density to areas of low electron density. We're then left with our bromide ion because it received both electrons in that shared pair of electrons. And we have a curly arrow going from the lone pair on a bromide ion to that carbocation. Then from here, we have our dibromoethane. So we have our dibromoethane, guys. Just going through the mechanisms here. There's 7 key curly arrow mechanisms that you need to know for your exam. A lot of them are very similar. Remember, all of the electrophilic substitutions for benzene all follow the same mechanism, so don't get intimidated. It could be an unseen one, so don't get intimidated with that either. So there's your electrophilic addition, guys. Just going to be doing this for potentially 10 more minutes. 10 more minutes, guys. I've just been going over key mechanisms. Alright, guys, now we're going to focus on. Let's go for. If you guys have any requests for a mechanism, I'm happy to. What was it? Diamine, diace thing at the end called? Not sure what it is. Let me know if you guys have any questions. Any questions indeed. Just going through some key mechanisms, guys. If you're here for the key topics, we have finished the key topics. We're going to go over the nucleophilic addition mechanism, going from a. Let's go from a to aldehyde to a hydroxynitrile. Let's go for that, guys. Aldehyde to a hydroxynitrile. So we have our alkyl group here, bonded to a hydrogen. So what are the reactants that we need to go from an aldehyde to a hydroxynitrile? Ozone. I'll go over ozone after this one. Carbonyl plus Cn minus. So if we're going from a ketone or an aldehyde to a hydroxynitrile, we don't want to use HCN because it's highly toxic. We want to use sodium cyanide, acidified sodium cyanide. So we get those H plus ions. Let's just run through the mechanism, guys. Let's run through the mechanism and I think everything will become clear. So our cyanide ion has that lone pair of electrons. It's a nucleophile. That's why it's nucleophilic addition. We know we form a polar bond between our oxygen and our carbon because the oxygen is more. Oh, sorry, that should be a negative. Because the oxygen is more electronegative, we heterolytically break that double bond with both electrons from the pi bond going to that oxygen. And then we have we have a curly arrow from the lone pair of electrons on our cyanide ion attacking that partially positive carbon. So continuing on, guys, what have we formed? What have we formed? If it lets me. Okay, there we go. Yeah, I do apologize about OneNote. I'm trying my best to be fast. So that carbon is now single bonded to the oxygen because we broke that pi bond. It's negatively charged because it received a lone pair of electrons. We have our alkyl group. We then form that carbon-carbon bond to the cyanide ion to extend the carbon chain. Key thing to understand in these long mechanism questions. And then from there, what else did we have? We had a hydrogen. Now here's the key thing to remember, guys. So we are surrounded by protons. We're in acidified conditions. We're surrounded by protons. So what do we know? We're going to be surrounded by. I'm not sure why it's typing. We're going to be surrounded by H plus ions. So surrounded by H plus ions, we know we're making a hydroxynitrile. We're going to need the alcohol functional group. We have that curly arrow going from the lone pair of electrons on our oxygen to that positive hydrogen. And that will leave us with the exact product that we need, the hydroxynitrile. So that's exactly what we have. We have our carbon. We have the alkyl group. Well, that's horrendous. Alkyl group. We have now the alcohol functional group, still bonded to that hydrogen, and then bonded now to that cyanide ion. So we have indeed a hydroxynitrile. Important mechanism, guys, nucleophilic addition. Nucleophilic addition. I only know about OCRA, guys. I only know about OCRA. Exactly. So, okay, guys, tell me what we need for the reduction of a ketone Reduction of a ketone or an aldehyde. Reduction of a ketone or an aldehyde. Let me know what we need, and we're going to go over the mechanism for that. That's another nucleophilic addition mechanism. Another nucleophilic addition mechanism. So we're going to start off with a ketone. Let's go for an aldehyde as well. It doesn't matter, guys. It doesn't matter. Everything would be the same. We would just have. You know what? Let's just do a ketone here. So because we have a ketone, what do we have? Sodium borohydride. Exactly that, guys. Aqueous sodium borohydride. That's very important that it's aqueous because it will help us in this mechanism. So first thing we do, label our dipoles. We know that carbon is going to be partially positive and the oxygen is going to be partially negative. From here, same thing, exact same idea. We're going from aldehyde or ketone, so carbonyls, to the hydroxynitrile. We're going to be breaking, because our oxygen is more electronegative, we're going to break that pi bond heterolytically, breaking a covalent bond with both electrons in the shared pair of electrons going to one of the bonded atoms. And then remember why do we have it? It's nucleophilic addition. We need a nucleophile. Sodium borohydride provides us with those hydride ions. So we're surrounded by negative hydride ions. So those will have a lone pair of electrons, showing the movement of a lone pair of electrons from an area of high electron density to an area of low electron density. Oh my god. Okay. So then from here, we'll be forming very similar to our carbonyls to the hydroxynitrile mechanism, but continuing on. Now we currently go to have that carbon single bonded to the oxygen, negatively charged now because we broke that pi bond heterolytically. We still have all these are alkyl groups. They can be the same, they can be different, it does not matter. What did we combine? We combined with a hydrogen. Now, what do we remember, guys? What do we remember? We had aqueous sodium borohydride. Aqueous sodium borohydride. What does that mean? What does that mean? It means we're surrounded by water molecules. We're surrounded by water molecules. We know that water molecules are polar. Water molecules are indeed polar. Oxygen is more electronegative than our hydrogen. So we have these polar water molecules. Polar water molecules, we can have heterolytic fission, breaking of covalent bonds with both electrons in that shared pair of electrons. Oh, let me make sure it's in here. Going to one of the bonded atoms. Let's do this. And then from here, the lone pair of electrons on our negatively charged oxygen will attack that partially positive hydrogen. And then from here, what are we left with? Let's just see what we're left with. We now have that carbon now bonded to the alcohol. Oh. Now bonded to the alcohol. So we're going from a ketone here, guys. We had our alkyl groups. Horrible drawing, guys. Horrible, disgusting drawing, but the alkyl groups are not that important. We had that hydrogen, and what are we left over with? We also have, because we broke that water molecule, we're left with a hydroxide ion. My god, this is disgusting. With a hydroxide ion. That's nucleophilic addition for the reduction of ketone or an aldehyde to an alcohol. Very nice, very nice. Guys, let's keep going. Let's just keep going. Why not? Probably just go for a couple more minutes. Oh wait, someone wanted me to do ozone. Let's go over ozone very quickly. Free radical substitution. Going over ozone, we saw in our initiation, we had our halogen. Under UV light, we formed two chlorine radicals here. Forming two chlorine radicals, OCR uses tetraborohydride, sodium tetraborohydride. So with ozone, we have this equilibrium within ozone, O2 plus O, and O3 on the right. Free radicals are in the atmosphere. Now we're asking how CFCs lead to the destruction of ozone. The weaker CCl bond compared to the CF, because this has a lower bond enthalpy, broken by homolytic fission. So we're forming that free radical, one unpaired electron going to each of the bonded atoms, forming radicals. So this catalyzes the breakdown of ozone. Break that bond, we form our radicals. This could also be with NO2 going to an NO radical plus oxygen. Propagation, we then have our chlorine radical plus the O3 goes to ClO radical plus O2. Because remember, in our overall equation for the breaking down of ozone, we end with 2O2. Then we have our ClO radical plus that single oxygen to go to a single chlorine radical, reforming that catalyst because the chlorine radical catalyzes the breakdown of ozone. And then we have the second O2. CFCs are used as propellants, aerosols, refrigerants because of their stability. If we were to use this NO2 instead and form that NO radical, we would then have our NO2 radical with O3, go to an NO2 radical plus O2, still forming those two oxygens as the products, and O3 and O on the left, radicals, our NO2 radical and our NO radical. Nothing scary, guys. So I think that's it for today, guys. I think that's it. I wish you guys luck. We'll be back at 10 a.m. and we're going to go from, I believe we did polyamides. So we're going to go from ester hydrolysis and onwards. Ketone, nitrile, purifying organic solids, amide hydrolysis, and TLC and gas chromatography. Maybe I'll put on some past paper questions as well. But that's it. Hope everyone's feeling good. And that's it. Cheers, guys.